All right, let's jump right in. In our everyday lives, light almost always means heat, right? The sun warms your skin, a light bulb gets hot if you touch it. But what if we could just flip that completely on its head? What if you could use a beam of light not to heat something up, but to cool it down? To temperatures colder than the deepest parts of outer space.
It really does sound like science fiction, doesn't it? But this is the actual technology that makes some of today's most advanced physics possible. Now, if you were with us last time, you'll remember we talked about that super bizarre fifth state of matter, the Bose-Einstein condensate. Well, today, we're going to rewind a little and figure out the incredible tool that physicists had to invent just to get there.
The technique is called laser cooling, and it really is the foundation for creating all this ultra-cold matter. But it all starts with solving one really tricky problem. So, picture this. You've got a little cloud of atoms just floating around in a near-perfect vacuum. You want to make them colder. But how? All the ways we normally cool things down are suddenly completely useless.
And this gets us right to the heart of the challenge. See, to cool something down, you usually need to put it in contact with something colder. But in a vacuum, well, there's almost nothing there to transfer the heat to.
Think about it like this. You put a hot cup of coffee in the fridge. The coffee cools down because it's giving its heat away to the colder air to the walls of the fridge. But for our cloud of atoms in a vacuum, we've created this almost perfect isolation. So the very thing that helps us study them, getting them all alone, is exactly what stops us from cooling them down the normal way.
So physicists had to completely change their strategy. Instead of trying to pull heat out of the gas, they decided to directly attack the motion of the atoms themselves. Because at its heart, that's what temperature really is for a gas. It's just a measure of how fast its atoms are zipping and bouncing around. So the crucial insight is this. If you can slow the atoms down, you make the gas colder. Simple as that.
And this is where light comes into the picture. The solution was to use the momentum of a photon, a single particle of light, as a tiny but unbelievably effective brake.
And the secret ingredient that makes this brake work is a phenomenon you have absolutely experienced, the Doppler effect. We all know it from sound. You hear an ambulance coming towards you, the siren's pitch is high. As it passes and moves away, the pitch drops. Well, the exact same thing happens with light waves. Okay, now here's the really clever part. Physicists take a laser and they tune its frequency to be just a little bit lower than what an atom normally likes to absorb. So a stationary atom will just ignore it. But for an atom that's moving towards the laser, its own motion kind of squishes the light waves, which makes their frequency seem higher. That's the Doppler effect in action. The laser is tuned so that this new, higher frequency is now the perfect one for the atom to absorb. So bam! The atom absorbs the photon head-on, and that photon carries a tiny bit of momentum, delivering a little kick that slows the atom down.
Now, one little kick doesn't do much, but this process is absolutely relentless. The atom gets hit again and again, millions of times. Now, you might be thinking, doesn't the atom spit a photon back out? And yeah, it does, but it does so in a totally random direction. So over time, all those little outgoing kicks just cancel each other out. But the absorption is always from the same direction, acting like a constant brake. And the cumulative effect is just staggering. We're talking about dropping the atom speeds from that of a jet plane all the way down to a slow crawl.
Okay, so that's how you slow down an atom moving in one direction. But of course, atoms in a gas are moving randomly in every direction. So how on earth do you cool the entire cloud?
You build a trap made of light. Instead of just one laser, they use 6, all arranged in pairs, up and down, left and right, forwards and backwards. This creates what's brilliantly called optical molasses. Because no matter which way an atom tries to move, it runs smack into a laser beam that's tuned to slow it down. It's like the atoms get stuck in this thick, gooey grid of light.
Once the atoms have been slowed way down by the molasses, a magnetic trap gets switched on. And you can really just think of this as a magnetic bowl. It creates a field where all these slow, cold atoms naturally collect right at the bottom, holding them all together in a nice, chilly little cloud.
But even laser cooling isn't quite enough to get to those ridiculous temperatures needed for things like a Bose-Einstein condensate. So physicists add one final step, evaporative cooling. And it works exactly like steam rising from a hot drink. The fastest, most energetic water molecules are the ones that escape as steam, leaving the cooler ones behind. In the same way, physicists will carefully lower the sides of their magnetic bowl, which lets the very fastest, hottest atoms fly away. And what's left behind? An even colder cloud of atoms.
So, We've gone from this crazy, paradoxical idea all the way to a multi-stage process for creating some of the coldest stuff in the entire universe. But why? Why go to all this trouble? Well, this is where a cool lab trick turns into some seriously powerful real-world technology.
First off, just take a second to appreciate how cold this is. By repeating these steps, physicists can reach temperatures of just 1/1000th of a degree above absolute zero. That's the coldest temperature theoretically possible. It's a temperature that basically never occurs naturally anywhere in the cosmos.
And from this incredible cold, you get some incredible applications. This is the technology that makes Bose-Einstein condensates possible, which we talked about last time. It's the engine that drives the world's most precise atomic clocks. It's the basis for next-generation quantum sensors, and it's even making things like navigation systems better. And here's the fundamental reason why this matters so much. Remember, the temperature of a gas is just the random chaotic motion of its atoms. When you cool them to near absolute zero, that chaotic motion practically stops. An almost motionless atom is like a perfect, clean quantum system. And because they're so still, we can measure their properties without all the noise of them jiggling around. That leads to unbelievably accurate measurements. And that is the secret to making everything better.
So we've really seen how light can be turned into a brake for matter. And this isn't just some clever trick you do in a lab, it's a fundamental shift in our abilities. It allows us to not just observe the weird laws of the quantum world, but to actually harness them, to build them right into our tools.
We've built the foundation. We now know how to create a cloud of almost perfectly still atoms. Which of course raises the next big question. How do you turn that still, cold cloud into a device that can measure time so precisely it actually redefines our concept of a second? Well, that is exactly what we're going to get into in our next explainer.